I'm going to continually ground ourselves in vector spaces, but I'm going to do that just as a place to hold on to and not the only thing we can possibly do. And this generalization of sort of moving towards traces is also great because it respects so much structure, right? There's so many compatibilities that this has with like things you can do with vector spaces. So the very first thing is you always have cyclic invariance. Anything I'm going to have a trace called a trace really should be cyclic invariant. In many cases, traces are also additive, which is another thing we sort of really want in good invariance. Like I think we sort of believe that good invariance should be additive. I should be able to decompose them. And what I want to do today is talk about compatibility with tensor product or some sort of monoidal product. That's what I want to talk about today. And I want to primarily use this theorem I'm talking about as a vehicle to talk about ideas about duality. So I'm thinking about this more as a vehicle for the ideas that go into it than the theorem itself as being my central focus. And the motivating theorem, so I went back and looked at the original papers it came from, and I'm sure I'm not the only person who's had this experience. I'd spent so much time with those papers and then so much time away from them, the papers didn't say exactly what I thought they said anymore. I had morphed them and their proofs into a thing that was more useful for me. So I'm going to cite this theorem as coming from these particular people, but it's more following them than literally what appears in their paper. So just a heads up about that. So the theorem following Petit and Sklarov is we're going to let B be a smooth and proper DG K-algebra, M a finitely generated and projective right R module, N is going to be the same thing except it's going to be a right R op module. Then there are two statements. The first one is there is an interesting class, which I'll denote EU of M in the Hochschild homology of B. This is the thing I'm thinking of as the generalization of dimension. Yeah? What is the relation between K and R? Oh, B. So I've just noticed that my B turned into an R. It's a B. Thank you. Yeah. There is an interesting class in the Hochschild homology of B coming from this M. It should be thought of as a generalization of dimension, and I will define it for you, but right now it doesn't actually matter what it is. And so there's also a corresponding class for N in the Hochschild homology of B op. Right? And then the real content here is that if I take this Euler class of M and I pair it with the Euler class of N, that's the same thing as the Euler class of the tensor product, where I have to do two things. So one of them is, this is N regarded as a left B module. I had to switch the side, right? Or make that tensor product make sense. But I want the sides to be consistent when I'm defining that Euler characteristic, but I can definitely do this flip. And this is, there's a pairing on the Hochschild homology of B and the Hochschild homology of B up. So the theorem is saying that there is this really nice compatibility between the Euler characteristic of the tensor products and this familiar, in fact, pairing on the Hochschild homology of A or B and the Hochschild homology of B up. Yeah. Oh, you want me? Yes. I will move the board. There we go. Cool. Okay. So what I want to do is I want to tell you about a generalization of this theorem that does several things. So the first thing is I'm going to replace Euler class by a trace of a non-identity endomorphism. First thing I'm going to do. The second thing is there's actually a sort of sneaky asymmetry in here that I want to fix. There's a sidedness, right? There's a B module. It's not like an AB module, for example. So I want to fix that too. And the last thing I want to do is I want to take this out of the generality that I'm in right now. Right? I want to make a statement that's true far more generally. So I'm going to take us from algebras and their modules to monoidal bicategories. Because why not, right? That's where I'm going to take us. So this is my motivating theorem, and these are all the changes I want to make to it. And so now what I want to do is I want to tell you what the version I want is. So I can have them right next to each other. And in the interest of sort of sanity and less notation, I'm going to still pretend I'm in rings and modules, because I don't need the greater generality at this moment, but you should feel free to read that if that makes you happier. So now, A and B are going to be smooth and proper DGK algebras. M is a B bimodule that is finitely generated and projective as a B module. So I fixed half of my.
Sorry.
Yeah.
The equality in the second bullet, that's an equality that takes place where? So is it in some Hochschild homology of something, namely of what?
They end up in the ground field K.
Oh, I see.
Yeah.
So
they end up in
the right-hand side is this same type of Euler class, except interpreted with respect to the ground field K.
Yep, exactly. Yeah, because
Okay,
that's
thanks.
the structure that M tensor N has
Great.
at the end of the day. Yeah. Other questions? All right, so we have an AB my module that is finitely generated and projective as a B module. And then N is going to be an A op, B op bimodule that's finitely generated and projective as a B op module. So same setup as before. And now I get to have endomorphisms of M and N. So these are module homomorphisms. I want them to respect all the structure I have in place. I want them to be module homomorphisms with respect to the A and B actions. And so then there is a trace of F and G, which goes from, now it's a map from the Hochschild homology of A to the Hochschild homology of B. So this is my analog of the first bullet. There is a thing like this. And the trace of the map induced on Hochschild homology of A of the tensor of F and G, where I fixed the G action on, or the action of A and B on G again, so that I can actually tensor this way. So I flip the sidedness. Is, well, this is a map now, right? This is an endomorphism of the ground field because that's what structure I have left after I've done all this stuff. What it is it's a map from K to the Hochschild homology of A, tensor the Hochschild homology of A op, to the Hochschild homology of B, tensor the Hochschild homology of B op, to K. So this looks a little different because everybody has changed from being an element of K to an endomorphism, sort of as it should be, right? It really should be an endomorphism. So everything's switched to being maps. Well, this particular trace is this composite here. Now, who is everybody? Well, this is still the pairing from before. This is the pairing I wrote as cup. This is the trace of F, tensor the trace of G. And this is a thing I'm going to call a co-pairing. And from your assumptions that your algebras are smooth and proper, you actually get both a pairing map and a co-pairing map, right? The sort of structure just naturally gives you both of those. Now, this co-pairing map in the theorem above is just the familiar isomorphism from K to K tensor K. Right, that's all that thing is doing. So I'm just drawing that out here, making that very, very explicit. All right, so these theorems are in fact very similar. We've just replaced our identity maps by other endomorphisms, and we've taken our one-sided module to a two-sided module. All right, so this is the theorem I want to focus on, and what I'm going to actually do is I'm going to sort of take it apart and tell you what all the pieces are, and as I tell you what all the pieces are, I'll tell you sort of why it's true as well. All right, you'll see all that. All right, so now I want to go back to linear algebra, like seriously, all the way back to linear algebra. And I want to talk about the trace of a matrix. And so we're going to let K be a field, and V is a finite dimensional K vector space. And in my first understanding of what the trace of a matrix should be, I'm going to make my trace of a matrix just be a map from endomorphisms V down to K. I don't really like that for the reason I just indicated. I'd rather think about this as an endomorphism of K that sends my 1 to the endomorphism I'm interested in, and recognize that as my trace. Okay, well, I'd like to modify that a little more. Like, I'd like to look at, say, this composite. Oops, that's not what I'm doing. There we go. So, same deal. This still takes, say, an F and returns essentially the element of the field that is the trace. Right, so far so good. Haven't done anything super mysterious. All right, now I want to do something a little more mysterious. Now, if I'm in a finite dimensional situation, like I am, I always have a map from V tensor V dual to Hom VV. That's just true. If V is finite dimensional, this is an isomorphism. And I can actually tell you what these maps are. Well, this first one is evaluation. The bottom one's evaluation, right? That's all that thing does. This is just evaluation. All right, if you check and think about what that thing does, that check the composite. The top one is a little more offensive to me. So the reason that top one is offensive is I have to choose a basis, right? And we all should be very sad about this. This is going to go to the sum of VI tensor VI dual, where VI is a basis for V. Fine. Fine, we did it. All right? So this composite's actually going to be much better for our purposes. So this is the thing we sort of most originally encounter in our earliest interaction with what should trace be. It's that one. This far composite is the thing that's actually more useful for us. And that's the thing that's going to carry through and become the trace right here. Yeah?
Do we know that that sum is actually dependent on the choice of basis? Does it vary with different choices?
So Doug just asked if this sum varies depending on the choice of basis. So any choice of, let me say this is right. All choices of dual are isomorphic, and the isomorphism you choose will actually be compatible with these choices. And the end result of this whole composite is independent, but you do have to verify it. This is part of why it's offensive, right? Yeah, it's offensive. Okay, so this is good for our purposes, but still upsetting. So before I go on, I need to actually come clean about something here, that there's actually sort of a secret symmetry I've suppressed, and I really want to own that symmetry. So what I actually want So I actually want a map K into V tensor V dual, which I'm going to call eta. And I actually want a map from V dual tensor V down to K, which I'm going to call epsilon. So that just means that that evaluation map I had before, that's just going to have a symmetry tacked onto it. And the reason I want this is because in order to move this from vector spaces on, I need to impose a condition on these maps. They need to satisfy the triangle identities. And I can't do that really in the form that they're up there already. I can only do it in this form. And to write that down, I actually want to switch to pictures now too. All right, so at this point, I will stop doing this painful writing and I will start doing everything graphically. So at this point, I'm going to switch over and draw my eta and my epsilon this way. Okay, this is how I'm going to draw things forever after. So vertices are now maps, edges are now objects, in this case vector spaces. Drawing things stacked next to each other horizontally means I'm tensoring them. Vertical is going to be composition. The fact that there's nothing here means there's a secret unit or a secret K hiding out of there, a secret monoidal unit. So one of the reasons I want to do this is because it now becomes much easier to tell you what these triangle diagrams are. Well, this guy right here that introduces an eta and then cancels it with partially with an epsilon, that's going to have to be the identity on, I guess this is V. And I also want the same thing where the roles are reversed. I also want that to be the identity on V dual. And now I also want to mimic that picture above, right? I want to take that same composite and draw that. So then the trace is, well, is now this. I will not ever worry about what side my crossings go on. Crossings will just go whichever direction I feel like. So I'm very sorry if for grade group people, I will just cross in whichever direction I feel like.
Before your committee.
Is there a question?
Does Vice President Pence, who you just
Wait, there was a question, I think.
I heard Vice President Pence.
Okay, cool. Then we're good, I think. Or we're just really confused. So this is translating the last residue of translation I have to do. I have now done. So I have now fully switched from the top board to the bottom board here. Okay, so what this does for us, it gives us a notion of trace for dualizable objects in a symmetric monoidal category, right? That's what I've just described for you. An object with a companion object with morphisms like this that satisfy these triangle identities is a dualizable object in a monoidal category, and that is its trace. Now, for this theorem here, I'm actually interested in two generalizations of this. I need to take this two different directions. So the first direction I can do basically by reusing these pictures. So I'm going to go ahead and reuse these pictures. So what I'm going to do with this, and we're going to hope that the color comes through, is I am now going to color. Like this. Oops. And I want to notice that I have this beautifully colored picture and everything is still compatible, right? Nothing has gone wrong here. There's no sort of weird twisting. Colored regions are sort of entirely constrained by the edges I'm talking about. So everything is good graphically, right? Now, what did I just do? Well, I just took this definition and I just moved it from vector spaces to, say, rings and modules. Right, that's what I just did here. Because now what's happening is my regions now represent, say, rings or K algebras. My lines represent modules. And the colors on either side indicate the left and right actions I have. And my vertices, my nodes, indicate homomorphisms. So this now right here, for example, could become a map from A into M tensor over B with M dual. And this would be M dual tensor over A with M to B. All right, so I've just taken everything and moved it sort of up. This now gives a notion of dualizability for one cells in a bicategory, right? So our dualizability for objects in a symmetric monodal category just got moved up to a dualizability for one cells in a bicategory. So I got a problem. Oh, I should first say that finally generated projective modules definitely have this. Like, this is not a vacuous notion. There's actually a lot of things that are dualizable in this way. So we're actually okay, like this actually does happen. But we have a problem with my other picture, yeah? It's a rather serious problem, in fact. It's quite serious. So I can't actually fix that problem by just drawing on the board. I thought really hard about drawing this picture in a way that I could fix it, but then I thought you'd just not believe me when I drew it the first time, and that seemed like a poor choice. So what I want to do is I want to draw how to fix this first, and I want to follow the sort of graphical first and then tell you what it means approach. So I draw it graphically first. So what I'm going to do is I am going to move this onto a cylinder. So, and right now, I just want you to bear with me and be like, sure, that's a thing you could do. And we will notice, I used the pink and the blue. So, oops. We'll notice now that everything is fine, right? Everything is fine. So physically, everything looks good. So the question is, what did we add, right? What did we impose here to make this work? And what we did is we added, a functor So here, B is going to be, let's make this a little bit curlier. This is a bicategory. We had a functor that takes us from our endomorphism 1 and 2 cells down to somewhere else, somewhere fixed. I don't care where it is. It's usually going to dump in something very, very familiar, closely related to what we started with. And isomorphisms. I need to give a name to this. I'm going to use the conventional name, which is this double angle brackets. Satisfying some coherence. So this is the structure we have imposed. We have sort of forced everybody to live in the same place. Right? That's what we did when we sort of glued together on the outside. And we said we can sort of cycle things around. Right? So this comes from my thesis, and it's called a shadow. And it acts just like a trace, right? It has cyclic invariance just like a trace does. Okay, so now I just want to observe where we are right now. We now have traces and dualizability for one cells in bicategories. This trace is the trace right here, right there, right? This trace is, these two traces agree. They're the same traces. One of the most common ways you get this kind of structure is it's actually like, say, Hochschild homology, right? That's a thing that totally does this, right? In fact, that's the most common example I use in my life. This is Hochschild homology. But the next thing I want to do is I want to go back to this definition and use this to produce that kind of structure. All right, so that's the next thing I do. So I've now revisited this trace. Well, it started out here, We colored it, right? Lifted it up into a cylinder. Now I want to use this same idea to get at this kind of functor. And to do that, I'm now going to rotate the trace, the one I have here. Right? So we first colored it, and now we're going to rotate it. And in a hope to not get everyone horribly lost in the notation, I'm going to change the way I draw the picture a little bit. So it's going to be horizontal now, but all my nodes are also going to be rectangular. So this is, even though it's flipped, so like hopefully that's enough, I'm going to still do more. So now the pictures I want to look at are going to go like this. They're going to be really angular, right? And my goal here is to produce that kind of object, right? Because I'm going to need that kind of object along with this trace to get at this theorem. All of these pieces have to go together. All right, so now to give you a sense of how to interpret this picture, or before we do anything else, I want to help you interpret this picture. So let's go back to that rings example again, right? We always want to go back to that rings example. Okay, so there's no color here, right? We don't have that going on. All right, so I'm going to think about K-algebras. So edges now are K-algebras, right? Edges are K-algebras. Maybe I should write this. The boxes are modules. Now I need to tell you just a little bit about what's going on. So how do those modules correspond to the edges that come in and out of them? Well, if you have an edge coming in on your left, you are a module over that algebra on your left. If you have two edges coming in, you are a module over the tensor product, right? Because we're going to say that vertical stacking here is tensor. And horizontal composition is, well, horizontal concatenation is going to be tensor product over the rings. So so in this picture right here, I'm going to have a module that has just, say, a K action on the left, and say has an A tensor B action on the right. Then this guy right here is going to be a module with a left and right action by a single ring. This is just switching the order in which I think about those rings as being tensored. And then this is a module which has that A tensor B action on the left and just a K action on the right. Okay, so for example, I could think about that far left object as being, say, a ring A, regarded as a module over K on the left and A tensor A op on the right. I think about that middle thing as, say, an A tensor A or an A bimodule. And then on the far right again, I have a, again regarded as an A tensor A op module, but this time on the left. This is a very fancy way of writing the Hochschild homology, or a very opaque way of writing the Hochschild homology in that case, right? That's all I've done here, is I said, let's take our A's and move the two A and A op actions inside and take some crazy tensor product. So I'm thinking about this as a way of writing down Hochschild homology that's a little bit more general. All right, so with this one, notice I started with the trace first and not the duals. So now I want to go back and talk about what those duals should look like, right? So okay, now we get into me attempting to be very careful with color, and we see how it goes. All right. So the pictures we had before, meaning these pictures, are now going to become maps. Like this. So notice this is the same picture as before. I've just rotated it and made it angular, right? So this is going to mimic, so this right here mimics this guy, right? Except here we had an equality, and now I want to weaken things. I want that to be an isomorphism. And I'm going to do the same thing with the pink on top. So if I take this kind of structure over here, right, my dualizability is going to turn into these angular box things. My triangle identities are going to turn into isomorphisms. All right, so I'm taking the same structure before, moving it over here. This is going to give me a notion of dualizability for 0 cells in a monoidal bicategory. All right, so if we're keeping track of what we have dualizability for objects in a symmetric monoidal category, well, in a monoidal category. We have dualizability for 1 cells in a bicategory. And now we're talking about taking that same definition and moving it towards dualizability for 0 cells in a monoidal bicategory. Right, so taking the same idea and just popping it down different places, seeing what we get. So we want that kind of structure. We also get some compatibility between these two maps. If you look at it, you could think about adding on another purple box. So if I have a setup like this,
I'm told that the purple essentially like.
oh,
Luckily, the red is.
cool. Okay, so I will stop using the purple.
Okay.
I will take away the purple. How do they feel about the blue?
Also pretty light.
So these boxes right here, they're purple, but apparently they don't look purple. So I will be moving away from that purple. Yeah, absolutely. Yeah. No, I have some other colors and I will just keep experimenting until we find out what works. Absolutely. Yes, I'm glad to hear. Okay, so the purple is not good and the blue is not good. Cool. Cool. So notice if I have this kind of setup, I could get to this by introducing the top pairing of the purple and the red, or the bottom pairing of the purple and the red. I need those to agree. So there's some additional compatibility we get that we didn't have before. But this is the sort of the structure we need. All right, questions? Okay. So what this alone does for us is it gives us precisely that functor that I had above, that shadow functor, right? It gives us a way to sort of tack stuff on the ends and kill that A module structure, for example. Right? We can just tack that on and kill it. So we need a way to sort of slide things past each other, right? Get that symmetry isomorphism. And the first place I saw this was work of Bensby and Nadler. And so I want to draw their pictures for you. Oh, let's try some new colors. Well, no, I'm going to keep that red. Okay. So what we would be doing, how's the green? No, I got a no from here. How about orange? Okay, so I have like one color that works. Yeah, okay, well, you know what we're gonna do? We're gonna keep our red and then live with this orange, maybe. We'll see. Okay, so what I've told you I should do, if I wanted to apply that shadowy thing in this case, using the trace type definition, is I should do this, right? That M and that N stacked next to each other, that's tensor product. I tack this stuff on either end. That takes me down to, say, K module, or yeah, K modules in this case. But what I need to do is I need to slide the M and the N past each other, right? That's my goal here. All right, well, the way I'm going to do this is I'm going to make things much, much bigger. this one and this one. So now I have this additional sort of triangle identity that I can slide in. I just slide that right there. Now, this is hard to visualize, but what I'm doing is I'm going to now rearrange this. I want to draw the same picture, and I can draw the same picture, but the roles of M and N are going to be switched. And the red boxes, and the boxes we see either as pink or orange, and Germany apparently sees as white, those are also going to switch. All right, so this guy is going to become the very, very same picture, because I can just slide everything past each other. Except that should be an N. So if you think about what this is doing, what the sort of tensor product composition is doing, this is a completely valid rearrangement. There's actually an isomorphism here that takes, that pulls sort of the inner red one out and pushes the inner red one in. And then the way the symmetries then shift, we actually like shift that symmetry isomorphism from in front of this red guy to in front of this red guy. They slide right past each other. And then I can cancel these two because that was an isomorphism. Oops. So this structure gives us enough, right? It gives us enough things that we actually do get all that structure we need to define a trace.
Excuse me, is that last thing you do an arrow downward?
It is a downward facing arrow, yeah. It's an isomorphism. Yeah. Absolutely, that last thing is a downward facing arrow. And I should slide this up. Okay, so at this point, I've told you how to think about the trace. I've told you how to think about that Hochschild homology. You should think about it as this kind of composition. And it has exactly the kind of structure we need to define a trace. The sad news is, even though I've given you all this structure, I haven't actually given you enough. There's actually still more we need, which I am sorry to say, but the happy news is you've already essentially seen it before, right? So I'm going to keep that theorem and erase here. So the remaining piece you need to actually get at this theorem, because the thing you still don't have is you don't have the pairing and the co-pairing. And the thing I need to do is I need to combine the two definitions I've given you beyond the duality for objects in the symmetric monodal category. And I need to take that definition of dualizability for one cells, and I need to apply it to these guys. So now what I need to ask for is I need to ask for that, we need to ask that, let's see, this goes, well, that's lovely, I used it backwards, whatever. This and this are dualizable as one cells. So these guys arose as things recognizing the dualizability of someone else, but we need to ask for they themselves to also be dualizable, right? And what this is going to do is it's going to give us sort of 4 more pieces of structure, essentially. So what we get, so this gives, all right, I'm going to keep the same color boxes for their duals and add a star to them. We're going to hope that this keeps us not horribly confused. Okay. So, and when I draw a box like this, I mean my monoidal unit, that's the thing that lives in there. So I need a map from this guy to the red box to the red box with a star. So I need a red box with a star, right? That's my dual for my red thing. And I need a map from this guy to this. So these are the evaluation and the eta and epsilon, just what form they take in this case. I find it extremely confusing to keep track of how much structure I have, but in this case what I pick up is I pick up these two maps which satisfy the same triangle identities as we had in my first colored version. Right? So many layers of dualizability. That's just the way it is. And we also, for the orange and or white, depending on where you are, we get a map like this and a map like this. So notice they're flipped, right? They both have maps of the same sort of shape, but they're flipped, and that's because of the sidedness. This notion of dualizability is strongly sided. You should feel free, if it makes you happy, to think of these as surfaces. I am not going to attempt to draw that, but if you'd like to think about these maps as surfaces, please go for it. And so now I am finally at a point where I can tell you the last piece, and that is how the pairing map works. So the pairing map what we're going to do is we're going to assemble our orange and our red boxes. So we're going to have an orange box with a star in it next to a red box with a star on it. And then we're going to have another red and an orange. And this is going to be my Hochschild homology of A up and my Hochschild homology of A. Right? So there's something going on there in that using the starred version, this is a legit way to define the Hochschild homology of A up, but it's in fact totally fine. So then my pairing map, the first thing it's going to do is going to splice those two reds together using this map right here. Now there's some additional like weird twisting in there I don't need, so I'm going to just get rid of that. And then the last thing I have is, well, this maps down to this, just the ground object, the monoidal object there. And that's the pairing that I saw in this theorem right here. Notice I have two leftover maps. That's my copairing, right? So it very naturally comes from exactly that same structure. So at this point, and I am out of time, what I have done for you is defined everything in my theorem. What I am not going to do for you is I'm not going to show you how you actually disassemble all this, right? Because that's, well, it's not actually that bad. So the piece that's missing here that I haven't told you is there is one final fact about traces, and that is traces always are compatible with tensor products in that the trace of a tensor is the composite of the traces. And this theorem can in fact be understood as a composite of traces, right? So there's a stealth composite of traces actually hiding behind here. So that is where I will end with the statement of the theorem, but not its proof.
Thanks, Kate. Are there questions from the local audience?
You mentioned that there's this paper of Bensby and Nadler where they draw these pictures.
Yeah,
Could you say more which paper that is?
it's